All right, AP Physics people, we have one more electricity topic to talk about. And luckily, we're back here in room 324. I'm back united with my smartboard. Pretty excited about that. So hopefully the penmanship will be a little better in this particular video. The topic for today is capacitors, and capacitors in series and capacitors in parallel. So the first order of business would be, what exactly is a capacitor? Well, we've discussed parallel plates in the past, and you can see on the screen a set of parallel plates. And what one typically does is connect them to a cell or a battery. Here we have a battery shown. You can see the VB. If we take the negative side and hook it up to one plate, and we take the positive side and hook it up to the other plate, that means we're going to have a migration of electrons. Electrons will flow from the negative plate and will populate this plate. And electrons are going to want to flow toward the positive terminal of the battery. So electrons will leave the plate on the right, thus making it positively charged. Now notice it's not a complete circuit, but electrons are flowing from the battery and on the other side to the battery, but it's still not a complete circuit. So a capacitor by design is a broken circuit. So if we call the potential difference VB across the battery, we could put a voltmeter there, and let's say it's just picking a number, a 10-volt battery. One might ask, when does this whole thing stop? When will the charging stop? Well, before you begin to charge the plates, if you were to put a capacitor across the plates, it would have read 0 volts. But now that we begin charging up the plates and get negatives on one plate and positives on the other, you're going to start to get a potential difference across the plates. And basically, the battery will not be able to pump any more charge onto the negative plate once the potential difference across the battery is the same as the potential difference across the capacitor. So essentially, you're charging up the plates and making your own little 12-volt battery, because if you now disconnect the battery and just take your parallel plate arrangement with you, it could sort of behave like a cheap little battery. So basically, the charging will stop when the potential difference across the capacitor, which used to be 0, becomes equal to the potential difference across the battery. All right, so what would that curve look like? What if you took an empty capacitor and hooked a battery up to it and started charging the plates up? Well, hopefully, if you look back at the previous picture, hopefully you get the impression that electrons would go very quickly at first, and then it starts to become harder and harder to put more electrons on the negative plate because like charges repel. So the charging happens quickly at first, and then it slows down rapidly, and we still continue to add electrons. It just doesn't happen as quickly. The current to the plate goes down. So the typical charging pattern looks like this. This is now going to be the potential difference across the capacitor. It starts at 0, and then you begin the charging, and it ramps up really rapidly, and then it starts to flatten out. And this is going to go asymptotic to whatever the potential difference of the battery is. So according to this graph, it's going to approach but never actually get to the potential difference across the battery. So then you have your charged capacitor, and then later, let's say you connect it in a circuit. So you take your capacitor, and now that it's charged, that's the symbol for a capacitor, maybe run it through a resistor or a light bulb. Let's make it a lamp. And that lamp would be bright at first, and then it would start to get dim and it would go out, because once all the electrons run from one plate around to the other one, I mean, this is going to discharge much quicker than an actual battery would. A capacitor is going to discharge quite quickly. So how quickly will it discharge? Well, it's going to start up at VB, or as close to it as it can get. And those electrons are going to want to discharge very quickly at first because the like charges repel. They're going to want to get out of there. And it will fall off, and then near the end, it will slow down quite significantly. So the charging and discharging curves, which you'll learn about from your textbook tomorrow, have this general shape to them, and those get modeled with a particular curve type, and you'll be able to predict the potential difference across the capacitor. This was also the potential difference across the capacitor in both the charging and discharging curves. So what exactly is capacitance? What's the definition? Well, capacitance is the ability to store electric charge. The more charge you can store, the higher your capacitance value would be. So the official definition, the equation definition of capacitance is how much charge you can store per potential difference of the battery. So capacitance, to have a big capacitance, you want to be able to store lots of charge with a very little battery that you use to charge it with. So what are the unit of measure? Well, we're going to have coulombs in the numerator and volts in the denominator. So a coulomb per volt gets a fancy name. Notice we have Mr. Michael Faraday over here on the right. The unit, a coulomb per volt, is known as a farad, often abbreviated with just a capital F. So our example here says, calculate how much charge is stored on an 8.85 nanofarad capacitor when it's connected to 3,000 volts. So if we want to solve for Q, that would be Q equals VC, and the V would be 3,000 volts, and the capacitance is 8.85 times 10 to the negative 9 farads, and that will multiply out to 2.66 times 10 to the negative 5 capital C coulombs. All right, we also have an equation for the capacitance of a set of parallel plates. So if we take two parallel plates and put them a fixed distance apart, you've created a capacitor, and you calculate the capacitance with a constant. This is our permittivity constant. You may remember earlier in the year I showed you that K, which is used in electricity, is really 1 over 4 pi epsilon 0. Well, that's the same epsilon 0 here. It's the electricity permittivity constant. So here's the 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And it also depends on, physically, these two quantities. The area of the plate, this is the area of one plate. And both plates are assumed to be identical, but that's just the area of one plate, and that's going to be in square meters. And this would be the separation of the plates. And that's going to be in meters. So the larger the area, the greater the capacitance, and the smaller the distance, meaning the closer they are together, the greater the capacitance. Before we solve the example, let me just take you to the FET website. And notice we have a cell here connected to a parallel plate capacitor, and the little meter on the right, the green, is showing you the capacitance amount. So what I'd like to show you is if I drag this green arrow and change the plate area, as I make the plate area bigger, you can see the capacitance goes up, and as I make the plate area smaller, the capacitance goes down. And then also, if I want to increase capacitance, I could make the plates closer together. So if I don't change the plate area, if I slide them closer together, the capacitance goes up, and if I pull them further apart, the capacitance goes down. I can also show you the plate charging as well. So here, if we go up to positive 1.5 volts, as I ramp it up, you can see that the negatives would leave the negative side and go to the bottom plate, and the positives, that's where the little bump is on the battery, that becomes the positive plate because the negative charges leave that side. So what is the capacitance of a capacitor with plates that are 5 meters squared each and separated by 1 millimeter? So let's write our equation. Capacitance is epsilon 0 A over D. That will be 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And the area is going to be 5 square meters. You don't have to square it in your calculator. Somebody's already squared it for you. That's the answer, 5 square meters. And divide by the separation. Notice we have millimeters here, so that would be 0.001 meter. And if you run that through your calculator, you will get 4.425 times 10 to the negative 8, capital F farads. Now, what do we do with these capacitors? Well, typically in circuits, they get put, well, they can be alone in a circuit. They can also be put in series and parallel. So what we'll look at on the next two slides are what happens when you put them in series and parallel, and I think you'll find it pretty interesting. The potential difference rule will not bother you at all because Kirchhoff's second law says whatever you gain at the battery, whatever your VT is, you must lose that potential as you go around any complete loop, whether it's resistors, capacitors. So if you go around the loop, there are three things in your way. If you go around this way, you have to pass through three circuit elements, so the potential drops across those must add to the potential drop across the battery, just like with resistors. Now, oddly enough, the way capacitors work, if you think about it, if we end up with a charge of negative Q on this plate, that would leave you with positive Q on this plate. Now, where did that charge go? Well, it went up here to this plate, negative Q, positive Q, negative Q, positive Q. So really what happened, if you look outside of this rectangle that I'm drawing, you have a top plate and a bottom plate, both of which are Q. So basically, if you look at one of the capacitors, it had Q and negative Q. And if you look at now outside my green rectangle, you have Q and negative Q. So really what you've done is you've taken the plates of a capacitor and really moved them further apart, which ends up dropping your capacitance. So whenever you add more capacitors, you're really just making the two outside plates further apart, which lowers capacitance. So believe it or not, the rule is 1 over total capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. So when you put capacitors in series, they follow the same rule that the resistors did in parallel. So if you put two identical capacitors in parallel, it will be half the value of one of them. All those same tricks you learn for resistors, they still work with capacitors. All right, what happens when you put them in parallel? Well, the potential difference rule will not bother you one bit because according to Kirchhoff's second law, each of these loops must have the gains at the battery equal to the drops out in the loop. And you'll notice every time I draw a loop, I could do it in different colors. There's only one item in my way each time, which means they must all get the full potential difference. So V total equals V1 equals V2 equals V3. So what's the capacitance rule? Well, here's one good way to look at it. We used to have, if we just look at one capacitor, a pretty small area, but now that we've put several in parallel, if you trace these out, all those plates are really touching each other, which means they're one big plate. What happens if you make the plate area bigger? Well, according to our last equation, it makes the capacitance bigger. So when you put multiple capacitors in parallel, you are simply making your capacitance bigger. So it ends up following the same rule that resistors followed in series. So in parallel, if you have multiple capacitors, you simply use the addition rule. All right, we'll take a look at one example. And at least we'll find the C total here. So let's take a look at the C total. We have a series parallel combination circuit, and we have a 3 microfarad and a 1 microfarad and an 8 microfarad. And hopefully you can look at this and say, well, those two are in parallel. And so we can combine those, or sorry, those two are in series. We can combine those, and then whatever we get for that red circled area, that can be placed in parallel with the 8 microfarad. So what do we get when we put a 3 and a 1 microfarad in series? So we would do 1 over C total equals 1 over 3 microfarads plus 1 over 1 microfarad. So when you use your capacitance total rule for the 1 over equation, you should get a total capacitance of 0.75 farads, or microfarads, sorry. Now we have a 0.75 microfarad in parallel with an 8 microfarad. And what do we do there? Well, they're in parallel, so we could do the addition rule. So we have the 0.75 and the 8. So the total capacitance for the whole circuit will be 8.75 microfarads. Now, we'll skip the potential differences here. Let's go to the energy stored in capacitors. You have a couple of equations that you should know for capacitor energy. Capacitor energy, as this equation shows, so when you fully charge a capacitor to a potential difference V, the energy stored on the capacitor will be 1/2 QV, and we can get another equation out of it by taking our capacitance equation, C equals Q over V, which rearranges to Q equals VC. So if we take VC and put it in for Q, we will get 1/2 QV squared. Sorry, 1/2 CV squared. Because we're plugging in for the Q, VC, so we have V times C, so it'll be 1/2 CV squared. So that's a brief introduction to capacitors. And then there'll be more forthcoming out of your textbook to learn about the RC circuits and the charging and discharging. So hope you enjoyed the lesson.